Welcome back to our course on memory device technology for AI/ML computing. I am your instructor, Dr. Shubhadeep from the Electrical Engineering at IIT Hyderabad. So let us begin with a quick recall of what we did last time. So please remember, we saw what was the need for the evolution of the memory hierarchy. And also we saw the 6 important concepts that we need to be completely thorough with if we have to follow the next part of the course and understand what is the current advancements in memory hierarchy and memory technology. These are first, latency versus capacity, how quickly you can access data versus bit density, on-chip versus off-chip. Remember, this was with respect to whether the memory or the storage element is within the same die or chip as the CPU. It is next is memory versus storage. It is how recent the data is or how relevant the data is to current computation. So most relevant data is stored in memory, whereas storage is more for retention. Volatile versus non-volatile involves whether you are able to remember the data after power supply. Sequential versus random access is how quickly you can access data, whether you can do it randomly or you have to go in a particular sequence. And static versus dynamic RAM, which we will discuss in the further classes. Also, we looked at the memory hierarchy. The memory hierarchy was primarily arranged in a pyramidal structure to indicate that there is a trade-off between capacity, which increases as you go down in the memory hierarchy, but also what you suffer is with the latency. Okay. So in the previous lecture, if you remember carefully, we were looking at the evolution of memory hierarchy due to the computing needs with evolving computing needs. Today, we will cover a very important topic. Today, we will look at how the memory hierarchy has evolved, pushed by advances in device technology, primarily memory and storage technology. And that will give us a complete picture of why the memory hierarchy or memory systems are the way that they are in present day and how they are expected to evolve further in the future. Remember, this is a continuously evolving field. So the image that we have right in front of us, let me just bring out my laser pointer, is that of a D latch. As you know from your basic course in digital electronics, even combinational circuits can be arranged in feedback loops. As you can see in the SR latch diagram, they can be arranged in feedback loops to behave like memory elements. And this is how the earliest form of memory and storage elements were built using combinational logic and are still used in CPUs. Remember, when we are studying the memory hierarchy or the von Neumann architecture, we saw that there are a bunch of registers within the CPU. These latches are how those memory elements are built and organized. Why is that the case? Because as you can see, within just one clock cycle, you will be able to store and retrieve data from this particular latch. However, what is the trade-off? Look at the trade-off. Let's start counting the number of transistors that are being used to implement this simple D latch, which is storing just one bit of data. First, we start with the inverter. As you know, the inverter consists of 2 transistors, NMOS and PMOS, and a NAND flash consists of 4 transistors. So if you sum all of them together, you will see 16 plus 2, 4 into 4 plus 2, there will be 18 transistors just to store 1 bit of data. Please understand, Q and Q dash are complementary. So it is not 2 bits, it is just 1 bit of data. So although you do excellent in terms of the speed in just one clock cycle, you really suffer from large area requirements. And as you know, just in real estate, so in silicon technology, the more area you consume, more expensive your technology becomes. So cost and area are directly proportional. So what did people do? They evolved the latch to occupy as little space. And this was done by inventing the 6T SRAM cell. T here stands for transistors. 6 transistors SRAM cell, as you can see in this particular image. Do not be intimidated by these diagrams. We will look at registers, 6T transistors, 6 transistor SRAM cells in details. How do they function? What is the structure? What is the read, write and hold operations? We will look into details of this. Right now I am just giving you a top perspective, a top view. Okay. So the same concept when we implemented using just 6 transistors, 2 belonging to each of the inverters and then the access transistors at the 2 ends, we had a 6T SRAM cell where you compromise a little bit on speed, but area requirements came down drastically. Roughly you can say it became 1/3 of what you see previously. So in the same area now you can, the bit density is becoming 3 times. So you can store 3 times as much data. And this is the technology which is still used in your cache memories, your L1, L2 and L3 cache, right? But still the area requirements are not good enough to have large amount of data storage. And this is where Robert Dennard invented the 1T 1C DRAM cell in 1967. As you can see, the 1T 1C DRAM cell is consisting of a capacitor and a transistor. Therefore, the area requirements for such a cell becomes much smaller than even the 6T SRAM cell. Therefore, you are able to get much better area benefit, but the problem comes in the realm of latency and speed. As we had discussed in the previous class, always there will be a trade-off between speed and area. Because you were able to accommodate larger bit density and integrate more memory, these 1T 1C DRAM cells were implemented in the main memories, right? And they are the storage elements of main memory. Those who are not familiar, Robert Dennard is also the scientist from IBM who postulated for the first time the Dennard's law of transistor scaling. Okay, let's move ahead. With these basic technologies, we were able to start doing computation of some scale. And this is what the memory hierarchy of the 1980s looked like. You had the CPU, and the CPU also had the caches, the level 1 and level 2 caches. Within the CPUs, there is no need to mention the registers because they are essential to the operation of CPU. So we generally don't consider them as memory. So you had the CPUs with the registers, you had your L1, L2 caches, and you had your main memory of DRAM, which was implemented using a 1T 1C transistor capacitor pair, as we saw in the previous slide. However, if you see, the next element in the memory hierarchy happen to be your magnetic disks. The magnetic disks, if you have looked at any old computers, we are still using HDDs. These HDDs consist of magnetic disks and a magnetic read-write head. And this is essentially sequential access. Whereas RAM or DRAM was random access, disk was sequential access. This is why we spent a lot of time understanding sequential and random access with examples in the previous lecture. What do you expect when you have an interface which is interfacing between random access and serial access? There will be a big divide in the latency or access times, and this is what is indicated in this particular arrow. While the access time from DRAMs was around 60 nanoseconds, that from disks were 5 milliseconds. So how many orders of magnitude is this? 60 nanoseconds is 6 into 10 to the power of minus 8, whereas 5 milliseconds is 5 into 10 to the power of minus 3. So it is almost 5 orders of magnitude. There are 5 orders of magnitude difference between the DRAM and the magnetic disk. And this was the primary bottleneck when you were operating systems at 1980s. There was a big divide between the random access memory and the magnetic disk. Therefore, people realize that there is a lack of any device technology which can fill this gap in the memory hierarchy. Okay. All of this changed in early 2000s and 2010 because of the invention of the flash cell in 1980s by Masuka in Toshiba. So Toshiba used to be a very big semiconductor device company. It still is, but it has been now taken over by its American counterparts. But they were the first to invent the so-called flash cell. What is this flash cell? Look at the structure of the flash cell. It looks quite identical to the transistor, and it is. And that is what was revolutionary about the flash cell. That it is able to not remember, it's not memory, it is storage. It is able to store bits for a very long time using just one transistor. Since it is storing in just one transistor, you can understand that the area benefit that we get from flash cell is enormous. So remember, we started from around 18 transistors, came to 60 SRAM to 1T 1C, and now we are just on one transistor, 1T flash cell. The area requirements for storing data or the bit density was very, very high, and therefore the postulate was that it could be used for main memory, and this is what has happened. Currently, all your HDDs, your hard disk drives, are getting replaced by SSD, solid state drives, which are built using the flash storage cell. What was the trade-off? Flash storage cell, the speed of access is very low, and we will see why that is the case. So although in this big divide from previous generation, from the 1980s, you had a technology where you are able to fill part of the memory hierarchy using the flash cell as indicated over here. Still, there is a big divide in the latency times between the between the flash cell and the RAM cell. Okay, so although SSD and flash memory technology is quite bit dense, the bit density is very high, still there is lot of latency issues. This is what is indicated between the IO bottleneck between the DRAM and the NAND flash. So NAND flash is a implementation of sequential implementation of the flash memory. So NAND, where the flash cells are organized in a NAND kind of bit stream. We will discuss about that later. Now let's look at what is the reason why even the invention of the flash cell is not enough to meet the requirements or the of computational requirements, or it is not enough to fill the gap in the memory hierarchy between memory and storage. So the first thing that we need to look at when we compare DRAM and NAND is the cost per bit. As you can see, the cost per bit for DRAM is almost 7 to 8 times of that compared to the NAND flash cell. That is because while NAND flash cells can be integrated with much lower area because they just consist of one transistor, the same is not the case with DRAM because it is very difficult to scale the capacitive element of the 1T 1C cell. Just as we discussed some time back, area means money in silicon technology or in fabrication technology. This results to almost 7 to 8 orders of magnitude difference in the cost per bit between DRAM and NAND flash. Next thing that we need to look at is read and write latency. The read and write latency for DRAM is around 10 nanoseconds, whereas for NAND flash is in the order of hundreds of microseconds. Still almost 2 to 3 orders of magnitude difference. Why is this the case? This has got to do with the interface technology or the access technology, whereas DRAM, as the name suggests, is random access memory. So any bit in the DRAM memory can be accessed randomly. NAND flash access happens sequentially at the block level, and this results in huge amount of latency in NAND flash, almost 2 to 3 orders of magnitude compared to the DRAM. Of course, it is offsetted by much a larger bit density. The next thing that we want to look at is the cell endurance and data retention. So what is the meaning of cell endurance? The meaning of endurance per se is how many read-write cycles can a memory or storage element sustain before it fails. And as you can say that in DRAM it can sustain almost 10 to the power of 15 read and writes. In NAND it is only 10 to the power of 4 writes. Let us consider why this is important. Please remember, the DRAM is used as main memory. In the main memory, the idea is to store data which is most relevant or most frequently used. That means the data also is to be frequently written into and read out of. So it is necessary that it has very high endurance. Whereas in NAND flash, just recall, in main storage you store a photograph. How often do you go back and look at the photograph? Not that often. So it is okay if the storage element can have little less endurance compared to the memory element, because their data is stored for archival purposes, not for very frequent use. Recent NAND flash technology is able to also sustain almost 10 to the power of 6 writes. So even NAND flash technology is improving and evolving. Next very important thing to look at is data retention, and as you can see, I have highlighted cell endurance and data retention because generally they also come in pairs of trade-offs. So these pair of trade-offs are between cell endurance and data retention. While cell endurance is very important for memory, data retention becomes very critical for storage, and that is what we see. While a DRAM cell has to be refreshed very quickly within the order of a few seconds or milliseconds, NAND flash, once you store the data, it can retain it in a non-volatile fashion for almost 10 years. That is how the NAND flashes are being built. Next important parameter to look at is power per GB at maximum bandwidth, which is how much energy is being spent to read and write data from the DRAM or NAND flash. And because the NAND flash technology is sequential and DRAM technology is random access, the amount of energy as we discussed, for implementing random access memories, the complexity is also high, and therefore the amount of power it burns is also very high, right? And that is what is reflected, that in NAND flash technology, it is almost 1/4 the power to the power requirements to access the same amount of information is just 1/4. Finally, we discuss bandwidth, which will be directly correlated to your read and write latency speeds, which will be directly correlated to your access technology, random access versus sequential access. And therefore, bandwidth for DRAMs are several, a few orders of magnitude higher as compared to the NAND flash. When we look at DRAM, we will also look at integration technologies such as HBM to explain how we are able to get such high bandwidth or throughput from DRAMs. The essential point we wanted to make is, although NAND flash technology has proven a great boon and we are seeing faster and faster SSDs, still there is a big divide in the memory hierarchy, especially between DRAM and flash in terms of latency and throughput. And this is what the new class of memories, which is storage class memories, aim to circumvent. So several storage class memories, which are also called electronic non-volatile memories, are in research and production. So we have not yet come up with large scale products. It is still coming out. It is still in the domain of research and development. But the idea is very simple. As you can see, the working memory is SRAM and DRAM. SRAM is caches and DRAM is main memory. There is a big gap in latency between the DRAM and the NAND flash, and the idea of storage class memory is to bridge the gap. The idea of storage class memories is to have both low latency and high bit density, and this is what I have indicated over here. And if you are able to really achieve that, the strict definitions between memory and storage will soon start getting blurred. So what are the emerging non-volatile memories that we will be studying in the course? Generally, these two emerging non-volatile memories are simple two-terminal devices. Why are they two-terminal devices? Remember, we made improvements from the DRAM to NAND flash in bit density by replacing the 1T 1C structure with just a single transistor. Now imagine if we can replace a 3-terminal transistor with just a 2-terminal memory element. Then the promise at least is that you will be able to get even better bit densities. You will be able to get even better bit densities, and this is generally done using a bunch of methods. So there is not one way of implementing non-volatile memories, emerging non-volatile memories. There are several different candidates, and all of them are based on the property of memristive behavior. Memristive means you try to exploit certain physical phenomena which alters the resistance between the two elements. It could be either magnetic MRAMs, which take care of, which exploit the spin of electrons, or resistive RRAMs, which use oxygen vacancies or conductive bridges, or they could be phase change memory, random access memories. Okay, so all these things we will be looking in detail further down the course. However, the idea is, while there was a significant improvement in the memory hierarchy with the advent of the flash, in the future we will be able to further bridge this gap with storage class memories through emerging non-volatile memories, and be able to completely close the gap between the between memory and storage. Okay, so with this, let us conclude. In this particular lecture, we saw how advances in memory device technology has enabled better, faster computational systems with better throughputs, better speeds. We started with 18 transistor register latch delatch circuit, which was taking 18 transistors to store just one bit of data. We went to 60 SRAM, then we went to 1T 1C, to just 1T flash cell, and then we are looking ahead in the future with 2 terminal memories. But please remember, nothing comes for free. As you reduce the area and improve the bit density, the latency times also start increasing, which is not necessarily a bad thing. They can be used for different elements within the memory hierarchy. Okay, so with this, let's conclude this lecture. In the next lecture, we will have our final understanding of memory hierarchy, and we will review how the different definitions of on-chip, off-chip, volatile, non-volatile fit into the pyramidal memory hierarchy. Thank you.